Jason has 20 years of experience in the restoration and protection of reinforced concrete structures. He has wide-ranging knowledge related to corrosion of reinforcing steel, cathodic protection installation, concrete condition assessment, concrete repair and restoration, and he's a certified NACE cathodic protection engineer. So welcome, Jason. That was good to stay.
Thanks, Dan. Good morning. Thank you, guys. Thanks for coming. So as Dan said, there's a couple of things that are basically a few things that I'm going to talk about this morning. I'm going to just get into the basics of corrosion, how it happens, why it happens. I think it's just a good base for everybody to kind of just get a minor or a little bit of an understanding of why it occurs. Because if you can understand why it occurs, then you're going to understand more of the solutions or the different products or solutions that are available for it. And then what I'm going to do is I'm going to be mostly talking here about substructures. So I'm going to go through the different elements or the different areas within a substructure and what methods or what tools are available for protecting or extending the service life of these various elements on the structure. And as well with that, then I'm going to talk about the different types of systems. So there's a number of systems. I'm going to go through a few of them here, but just remember, these are not. This is not a complete package of everything that's available out there. So the majority of the things that I'm going to be talking about here, just because I think it's going to be easier, and I have some good examples of it, is galvanic systems. There are powered systems that are available that will do the same thing. I just think it's going to be easier for me to just present it here, like I said, with some of the galvanic systems. So what is a corrosion cell, or why does reinforcing steel corrode in concrete? You know, you build a structure, you obviously put your reinforcing steel in there and you walk away and you come back, and a number of years later it's corroding. So why does that happen? And so if anybody can tell, this is actually a little salt shaker in a question mark here. And so typically in all the environments that we're involved in, it's usually due to some sort of a chloride attack or chloride concentrations that occur in the concrete. So here I'm just going to use this as a basic example. So what we have is we have a concrete slab. We have two mats of steel, top mat and a bottom mat of steel. And one thing to note is reinforcing steel in new concrete. New concrete has a high pH, and there's actually this passive oxide layer or a protective layer that protects your reinforcing steel. And so reinforcing steel in new concrete will not corrode. But actually over time, what ends up happening, so in this example here, we're going to have could be de-icing salts, it could be chlorides from a marine environment, but whatever it is, we're going to have some contamination that occurs over a number of years. So the chlorides penetrate the concrete. They make it to your first mat of steel in this example. And what they end up doing here is it basically breaks down this protective layer or this passive oxide layer that you have around your reinforcing steel. And once that happens, you essentially have two different environments. So your top mat of steel is in a chloride contaminated environment. Your bottom mat of steel is in a high pH, no chlorides, and you create this corrosion cell. And you end up getting this chemical reaction that occurs, and your top mat of steel becomes your anode, your bottom mat of steel becomes your cathode, and everybody knows what happens after that. You end up getting rust. And depending on who you talk to, everybody will agree on this: rust expands. Rust will expand anywhere from 7 to 10 times the amount, depending on what type of steel you have in there. But you end up getting the swelling occurs, the rust expands, then you get your spalling, your cracking, your delamination, and this process accelerates over time. So once you start to see this process, you get these cracks, more moisture can get in, more chlorides can get in, and it just accelerates over time. So this is just a short video demonstrating what happens. So you have these red dots are your chloride ions. They're penetrating your concrete, they get down to your mat of steel, and it breaks down this protective layer, and now corrosion can occur, and you can see it accelerates over time. So it gets much quicker towards the end or once you have a significant amount of chlorides in there. One of the things I want to talk about too is, I think it's good to understand this, is what is an electrolyte? And Because if you can understand what the electrolyte is, you can understand what type of systems and why you might pick one system over another system, or for a specific area on a structure. And it's not Gatorade, and even though apparently there are electrolytes in Gatorade. But basically an electrolyte is a medium, or it's a conductive medium that allows the ions to flow, or allows the current to pass through this, basically through this circuit. And so every type of, whether it's a galvanic system, an impressed current system, or a powered system, there has to be some sort of a medium, or there has to be some sort of electrolyte that's going to allow this chemical process or this chemical reaction to occur. And like I said, I think it's kind of important to understand this, because there's various systems that you're going to pick and choose for different parts of your structures for different reasons. And a lot of times it comes down to what type of an electrolyte or what type of an environment you're putting this anode in. So here's just a little diagram of a substructure. And so, you know, we have our piles, our pier cap, our columns, and our footers here. And so what I'm going to talk about is just the different environments that this substructure is going to be exposed to. So down below, the blue stuff is obviously our water. And so everything below this tidal zone, I'm going to call it the wet zone. So this is an area that's always submerged. You know, it's exposed to, typically, of course, in a seawater environment, it's going to be exposed to chlorides. It's going to be a minimal amount of oxygen that's available, or dissolved oxygen that's available. The next area that we have is our tidal zone. So obviously you have tides, so you're going to have water coming up and down, and you're going to be exposed to oxygen, and it's going to be wetted and dried over and over, you know, throughout a cycle during the day. The other area that we have above this is our splash zone. So obviously, depending on the location and the area where this substructure is, there's going to be periodic splashing, and it can just be due to wind, waves, and it could actually even be due to boat traffic as well. And the other area, or the other environment in the substructure is, I call it our airborne environment. So this is obviously an area that is not exposed to moisture directly from the water, from splashing. It's not being submerged. So in this example, there's four environments, and on the average, typically what happens is the lower areas are going to be more active, or you're going to see corrosion occurring quicker or more accelerated in these lower environments. The only exception to this rule would be more the wet environment. In the wet environment, you have less oxygen that's available, so you typically don't have real aggressive corrosion occurring here, but I couldn't draw the arrow properly for it, so I had to keep it this way. So for protection for our wet zone, I'm going to start on the bottom and work our way up. So for our wet zones, what are we going to do for these areas that are below the water line, below this tidal zone? What options are available for protecting these areas? These areas, like I had said, they're submerged areas. They're always submerged in water, so there's always chlorides that are present. And as I mentioned, there's lower levels of oxygen present. One of the other examples is, the parts of a structure is you have your concrete piles or concrete structure, but you can also, this is also, this type of CP or protection can also be used on sheet pile walls. It's a really common thing to be used on sheet pile walls, mainly probably in a port environment, but I just thought I'd mention that. And what we use for these areas are just bulk anodes, and they consist of just a large cast anode. And typically in a seawater environment, they're going to be an aluminum anode. It just performs better. It's more efficient in a seawater environment. But you can also use a zinc anode. So on the top right, we have a bulk zinc anode. This is your typical 48 or 50-pound bulk zinc anode, and it has some hardware. It's basically just strapped to the bottom of a pile in this wet zone, and there's a wire that's actually directly connected to your reinforcing steel. And there's a number of ways of connecting this. So usually a junction box is used, and it's going to provide cathodic protection or galvanic protection to everything that's in this water or below the water. On the bottom left, there's some bulk anodes here. These are typical anodes that are used on sheet pile wall, and they can be directly connected, usually welded to a sheet pile wall. So these are very simple, easy to install. Of course, they require divers. to install. And the next zone I'm going to talk about is our tidal zone. So typically this zone here is our most aggressive zone. It has a lot of moisture. It's exposed to a lot of chlorides, so it's wet and dry throughout, obviously through the tidal fluctuations during the day. There's lots of oxygen present, and of course there's lots of chlorides. Even in a brackish water environment, there's chlorides that are present. And so you can see here, obviously this is where the tide on the picture on the right, this is where the tide's going up and down, and you can see the corrosion that's taking place. And I'm sure everybody's kind of seen this. You get that hourglass shape on these concrete piles. And this can also happen on steel piles as well. This is also an aggressive environment as well for steel piles. So the solution in this environment is a pretty standard solution. It's been used for a number of years, and what it consists of is there's just a bare zinc anode inside of a stay-in-place form. And typically it's a fiberglass form, it's a stay-in-place form, it's placed around a pile, and this bare zinc mesh, typically it's a mesh, is going to be in there, and it's going to provide protection to this pile in this splash zone. So here's just a couple of examples of a typical jacket, a bare zinc jacket that you'll see. And in this example, when I was talking about electrolytes, well, you need an electrolyte to keep an anode actively corroding. So for this type of a system, I call it a bare zinc anode, we have our salt water that's available. This salt water is going to keep this zinc actively corroding, and it's going to allow this zinc to keep passing current to protect our reinforcing steel, or our cathode in this example. And so they can also be referred to as seawater activated as well. And so they're installed around a pile. There's a number of different methods and ways you can do it, just depending on how the contractor wants to do it. But it's a fiberglass form, so it can be a square jacket, it can be a round jacket, and you're going to need some sort of bracing or some sort of support, and then you're going to pump this jacket. You're going to fill it up with grout, with just a standard concrete grout. And so this was just a mock-up of a jacket. And here's one that's actually being poured. And you can see the hose, the guy's pumping in. And so typically they're going to start from the bottom, and they're going to move the hose up as they go, and they're going to tremie it. And some of these jackets can be below water, and they're going to tremie it, and the water's just going to come out of the top of the jacket. And once the jacket's full, they'll stop pumping and move on to the next jacket. And once the jacket has, once the concrete is cured, you're going to come back and just remove the jacket, and you're going to leave this fiberglass stay-in-place form there. And as the tide goes up and down, you're going to have this seawater in there that's going to keep this, basically it's going to keep this jacket activated. It's going to create an environment in there that it's going to be a nice electrolyte, and so you're going to have a lot of current, or you're going to have a significant amount of current that's present to protect this, protect the piles. The next area I'm going to talk about is splash zones. So these are typically areas that are above the tidal zone, outside of this zone, so you don't have this periodic wetting, or this daily wetting, or this wet and dry cycle throughout the day to provide this activation, or to keep your zinc actively corroding. And so these areas here, obviously it's through, like I mentioned previously, was either through waves, wind, boat traffic. So there is, there are chlorides present, there is moisture, there's oxygen. It's slightly reduced compared to what we have in our tidal zone. And this is just an example picture showing here where of a splash zone. And so there's a number of different ways. These are similar systems to the bare zinc anode jacket that I was talking about. The only difference here is these jacket systems, the anode in it is a self-activated anode. So there can be strip systems, as you can see here in the middle. There's panel systems as well that can be applied to the structure. And all of these different types of jackets, they can be custom made, they can be round, they can be square, they can be rectangle. There's a number of different things that they can do. Another area where these can be used in is brackish water. So brackish water, with a bare zinc anode in a traditional jacket, it might not be able to produce enough current. So your electrolyte, you have reduced chlorides in there. You might not have enough current within this tidal zone, or enough conductivity in this tidal zone to produce enough current. So you can also use this type of a self-activated jacket in a brackish water zone as well. So So this is just a couple of pictures of one of the systems being installed. So you'll go in, of course you're going to have some delaminated concrete. Any repairs that you have to do, you're going to come in and you're going to remove any of this delaminated concrete. All of these systems that I've talked about as well, you're going to want to make sure that all of your steel within your structure is continuous. So there's a number of different tests or checks that you can do to come in and just make sure your steel is continuous. If your steel isn't continuous, you're only going to be protecting what your anode or what your CP system is protected to. And this is typically, I mean, it's a fairly easy check to do, and this is something the contractor is going to do and then be verified by a CP specialist. So here they've removed the concrete and they're ready to basically install this self-activated jacket system. And then they come in and you put this jacket system around it just like you do in a wet zone, and you're going to provide your braces or some sort of shoring, and you're going to pump it, fill this jacket system up, and once it's done you're going to remove it, and now you have this stay-in-place self-activated system that's going to protect this splash zone. And as I mentioned, so now you have the self-activated anode that's in there, so you don't require the seawater to keep this active or to keep this anode actively corroding and providing a current. It's just another couple pictures of it installed. And see, we're only trying to protect this lower portion. There's no reason for us to go up higher. Here, we're only trying to protect this splash zone. Another area where this can be used in is pile caps. You'll see a lot of pile caps that are closer to the water, and they get periodic wetting or splashed, and there's various systems as well for this. They're an activated system, and traditionally they're installed and they're put in an overbuild and poured back as well. So like I said, there's a number of different systems that are available, and there's also, as I mentioned before, there's also powered systems or impressed current systems that are available for this. The last area that I'm going to talk about is the airborne zone. This is the area that's outside of these wet zones or even the periodic splashed zones. And these are obviously higher up on a structure, and these are probably some of the most noticeable zones as well when you're under a structure, and sometimes they're the hardest to get to as far as accessibility and so forth. But there's chlorides that are present, and everybody has seen this. If you've ever been on the beach, go to the beach, and if there's waves and the waves are crashing, you're going to see this mist blowing across the beach, and it's just basically it's a salt mist. It's a very humid mist, and there's a lot of salt and chlorides that are present in this, and this is part of what this structure is exposed to. So there's a lot of chlorides in here. There is moisture available, but it's not being wet. So in this environment, we can choose to use a different type of a system. There's no reason for us to come up and install some sort of a jacket system around it, because we're not, we have basically it's a different, it's up higher. There's typically larger areas. These are pile caps that we're trying to protect as well. So an easy method for protecting these areas, if it hasn't been extremely aggressive and you've caught it, if there's just some small repairs that can be done, you can come in and install some discrete anodes. These anodes are just installed in patch repairs. They're typically just for localized protection. You're not going to come in for the most part and try to protect an entire cap with these things, but you're going to come in and doing just some regular maintenance or repairs. And these can be effective if you're coming in and catching it at an early time. It's just another picture of a pile cap. You know, the deterioration, you typically see it on the bottom, on the corners, because it's got exposure to two sides, and you get that corner spalling off. And you just come in to install these discrete anodes in the location. They're going to be spaced out depending on the volume or the amount of steel you have in this structure, and then you're just going to pour it back. You're just going to do your standard concrete repair. And then another area, this is popular. Florida DOT does a lot of this. It works really well, and it's a fairly easy solution, and is metalizing. It's a metalizing spray, and what this is, it's a surface applied. It's a molten zinc that's basically, it's sprayed or blown onto the surface of the concrete. So it's a surface applied galvanic anode that's applied. It can be applied either to local areas. So if you have hot spots such as beam ends, you might have an expansion joint that's exposed to a lot of moisture, and a lot of times you'll have some accelerated corrosion that's occurring at the end of these beam ends. you can protect just the beam ends. There's no reason you don't have to go do the entire beam. Or you can also use this as a global protection system, so you can spray the entire pier cap, and you're going to provide protection to this entire top part of the structure. Again, it's a self-activated system. The salt mist is going to keep this metalizing spray actively corroding or actively applying a current to your reinforcing steel. And again, it's fairly easy to apply. So here it's just a nozzle. The guy has a nozzle here, he's spraying it on, so you have a power supply. Essentially what it is a wire feed, large wire feed welder, and you have basically two hoses. You have some zinc that's coming up, it arcs, it melts, and then you have compressed air behind it, and it blows it on the surface, and it looks like a zinc-clad paint when you're done with it. So there's a number of passes that are required for this to get a certain thickness, because you want to have a certain amount of or a quantity of anode that's available to it. So it's just another example of it being used in an airborne zone, protecting it. And just another picture of it, so you can see the equipment in the background there. And then this is a typical piece of the equipment that's used. So like I had mentioned, it's just a large wire feed welder, and the power source isn't here, so it's a larger DC power source that's going to be hooked up to this to provide the current, so that the metalizing spray, or sorry, the metal, the zinc can be melted. So it's probably hard to see in this picture, but you can see on the right side there's metalizing's been applied, and on the left side it hasn't been applied. And so once you do one pass, it's actually very difficult to tell how much you've applied to it. So there's a number of different techniques that they use to make sure that the thickness of this metalizing spray is appropriate for the lifespan that they're trying to protect the structure with. And that's basically it. So in summary, you know, there's a number, I know I only talked about galvanic systems here, but there's a number of different systems that are available, you know, powered system, impress current systems, galvanic systems, and a number of others that I didn't even talk about here. And one of the things to think about as well is there's obviously there's different parts of the structure that you're trying to protect. And not one system is going to be applicable to all of these areas. You know, metalizing spray works really well up in the top areas in this airborne environment, but when you put metalizing spray down in that splash zone, you now have wet, high chloride water that's splashing on there, and it's going to create a very, very aggressive or active environment. So you have a lot of corrosion or self-corrosion of your metalizing spray, and you can have a shortened lifespan for it. In the same sense as, you know, you could do basically that encasement system all the way up to the top of these to the substructure, but it's going to require a lot of work. It's going to require a lot of labor, and it's going to be difficult to do. And so the metalizing spray works well there. And at the same time, you can't use metalizing spray underwater. So all of these different areas, there's different solutions that are available for it, and I think it's just good for everybody to have some knowledge as to where these are applicable and why they're being used in these areas. So. And the last one as well, you can specifically protect just a very small area, or you can go in and globally protect an entire structure. So that's it. Thank you, guys.